Here I have an example of a projectile motion problem. It's not the same as the ones on the test review, but it is pretty close, at least similar enough to get some practice out of it. We have a basketball player who's shooting a basketball from eye level. Suppose that the eye level is 5 foot 10 inches. The ball is tossed with an initial velocity of 28 feet per second at an angle of 45 degrees to the horizontal. So as usual, the first thing I like to do is draw a picture because I can label it and look for what I have and what I need at various points in the problem. So I have a basketball player, and this person is throwing the basketball from eye level. The ball is going to go up in the air and then come back down. It's going up at an angle of 45 degrees initially, with an initial velocity of 28 feet per second. And then finally, the last thing I know is that the height above the ground when they first throw the ball is 5 foot 10 inches. So that would be 5 and 10 over 12 feet. And so there's my diagram. Here's my x-axis across. And there's my ball. Okay, so the first question that we typically ask is to actually make the two parametric equations, of course. So our first one is x, and again, these will be given to you when you get to your test, but there's our x equation, so we just need to fill in the blanks. We have an initial velocity and we have an angle, so we've got everything that we need. And cosine of 45 is square root of 2 over 2. So when I simplify that down, there's my x formula. The y one is a little bit longer, but again, not to worry, it will be given to you. All right, and g, for these purposes, since we're working in feet, is going to be 32 feet per second squared. So filling that in, along with the initial velocity, angle, and the initial height. Now, I can leave this as a fraction for now. I can even actually just make it a mixed number, or not a mixed number, but an improper fraction, because I want to keep it as exact as possible until I actually plug this into my calculator, so I'm not rounding a couple of times along the way. Okay, so here's my two formulas. There's the x and there's the y. Now, a couple things to remember. The x is always going to tell you the distance away from the start, and y is always going to tell you the height. So if I label that on this graph, I have the x along the x-axis and y along the y-axis. Again, when we have parametrics and we graph them, we're actually losing the t information. The t is embedded in that arc. We can only find it by using our equations because the scale is not built into the graph. So what we're looking at is horizontal distance away from the person and vertical distance up in the air away from the ground. Okay, so next question we normally ask is how long was the ball in the air before it bounced and hit the ground. We do have to assume that the person didn't hit the basket because that just adds a whole bunch of other variables. So assuming that they didn't touch anything, how long was the ball in the air? So we want to know how long did it take, how much time passed before it hit the ground. Now, one of the issues is we have two equations that both involve t. So we could technically use either one to solve for t. The problem is, though, we can't solve for t using the x equation because we don't know the distance. If that was given to us, we could definitely use and should definitely use the x equation, but we don't know that distance. So we have to look at our height equation and say, okay, do I know the height at that moment? And I certainly do. When you've touched the ground, your height would be 0. So since I know the height, I can plug in y here, and that allows me to solve for t. So my first question, we're going to plug in 0 for the y and solve for t. Now here, in this one especially, since I have a radical and I have a fraction, it's not going to be factorable, or at least not easily factorable. So I would prefer to use quadratic formula just because the time it would take for me to do completing the square, factoring, solving for that, I probably could have already done it using quadratic formula. So that's just my preference. You can certainly complete the square, but we have some decimals in here. So solving for this using quadratic formula, t is our independent variable, so that's what it is giving us. Negative b plus or minus all of b squared for a c, all of that over 2a. Okay, and there's quite a bit of math I can do now to simplify this before I start plugging stuff in and getting decimals. So I'm going to work inside that square root. 14 times root 2 squared. So 14 squared gives me 196, and then 2 squared gives me 2. So 196 times 2 gives me 392. And then here we've got a double negative. So 4 times 16 is 64. 64 does not quite divide with 12, but I can actually, let's see, we'll do 64, 70 over 12. I can actually reduce that. So if I divide by 4, that gives me 3 and 16, and that just gives me some smaller numbers to work with. And then on bottom, negative 32. Okay. So now doing a little bit more cleanup. 16 times 70 divided by 3. I'm going to get a number, at least it has a repeating decimal, so we're not doing too much damage by rounding. This comes out to be all of this right here, 373.3 repeating, plus 392 gives me inside 765.3 repeating. And as usual, I'm writing a lot more than you need to necessarily, just so you can see all of the steps that I'm doing in my head, but there are some places where I could have skipped a few steps to keep it simple. If I square root this, I get 27.6646. So I'm going to keep the decimal a little bit long for now so that when I'm doing that final division, I'm not rounding ahead of time and then rounding afterwards. Okay, so now the second thing I'm going to look at is there's actually two solutions here. You can solve for both, or you can take only the negative answer out of these two instead of the plus minus, just taking the negative one. That should always be your bigger number. But for these purposes, to show you the two solutions, I'm going to go ahead and solve for both. So the first one is going to be the plus, the second one is going to be the minus. So I'm going to take 14 times the square root of 2. Not the easiest thing to do on my computer. That gives me negative 0.246 seconds, or the negative version of that, .483 seconds. Okay, so we have a negative and we have a positive, and those represent the two ends of the parabola. So here, if I drew the other half of the parabola that is mathematically present in our equations, but not physically present in the real world, this is giving us that negative time. That's the negative 0.24. This entire thing is giving us that positive 1.48. So that's the time that has passed. This is going back in time and this is going forward in time. So this is definitely our correct answer. That one is useful for drawing the parabola, but not useful for our problem. Okay, so then the follow-up question might be, when did it reach the maximum height? When being a question about time, and what was that maximum height, meaning what was the actual height at that particular time. Now here, when we're asking about max height, a couple of key things. When we say height, that means that we're going to be using the height formula. So we need to use y equation, not the x still. And then maximum means vertex. So we're looking for the vertex of the y equation. So here's our y equation. Vertices always occur at an x value of negative b over 2a. Now x being the independent variable, so in this case that's actually a t. This always finds your vertex. If your graph is symmetric, where both ends are present on the positive x-axis, then yes, you can cut your time in half. But in this case, since time started here, not here, if I cut that in half, it's actually going to be a little bit lopsided and not quite at the vertex. So I don't want to do that all the time. It can be a shortcut if you know that your graph shows up on the positive x and we're starting at exactly the moment it was on the ground. But in general, this will always work. So I'm going to use that to find my time at the vertex. So plugging in the b and the a from the y equation, again, we're using the height formula, negative 14 root 2 over negative 32. And again, just a matter of plugging that into a calculator. I get 0.62 seconds. Hopefully everybody out there is checking my work. Since I'm working on a calculator on a computer, it's not the easiest thing to work with. So that's what I got for my time. That tells me the t value of that vertex, but I still need the maximum height itself. So that would give me the y value. And in order to find the y, you need a t, which we just found. So plugging that back in, I'm basically finding the y part of my vertex. And so now we just need to plug all of that into our calculator. Okay, so this is what I got, and again, hopefully you are checking my work, but that looks about accurate. If I go ahead and plot that on my graph, it's saying that the vertex occurred at 0.62 seconds, and the height was 11.95. Now, it might be important to write in t and y because it's not the x value, but it's the t value when that occurred. But now if we need to find anything about the distance, we could actually plug in that t value if that's the point we're looking for. So we could ask a bunch of different follow-up questions like how far away was the ball when it reached the maximum height? Or we could ask how far away did the ball go? In fact, we can try both of those really quickly. Anything asking about distance from the person is looking to use the x formula. So I'm actually going to do both since we haven't used the x formula at all. So the first question is, how far away was the ball when it reached the maximum height? So again, distance uses the x formula. And in order to solve for x, we need a t. So that maximum height occurred when t was 0.62. So to find the distance, it's just a matter of plugging in the 0.62 into that formula. And that would give me 12.28 feet away from the player. So after it had traveled almost 12.5 feet away from him, that's when it was at its maximum height. Then we might also ask a question something like, how far away from the person was the ball when it landed on the ground. So that again is asking about this point, and we actually already found the t for that one. T at that moment was equal to 1.483. And so we could ask about that distance as well, and it's exactly the same process because we have the t already, so we're just plugging in any t we want to find the distance away at that moment. Oops, I didn't mean to write that again. I thought I had something else to do. Okay, let's just plug that in. So that was a distance of 29.36 feet. And of course, in a basketball court, the ball would keep rolling, but that at least tells us when it landed. I think that's about everything that we could ask. The important parts are to remember that X tells you distance and Y tells you height, and T is just time. So if we ask something like how long or when did something happen, we're solving for T. Match the equation that you're going to use with whatever the question is asking. So if it's asking about height, you know which one to use. And then maybe even draw a picture and label each point as you find it, because you can always refer back to that point to help you out with the next question that we ask. As usual, if you have any questions, follow up, you can leave a comment and I will see it, or send me an email and I will respond.